Hello, my name is Teodora Bogdan, and I'm a research engineer at ArcelorMittal Global R&D. Today I will present you a paper related to the behavior of net arch bridges using heavy HD sections. More specifically, the experimental and numerical work conducted to understand the behavior of butt weld splices connections submitted to fatigue loading. The main objective of the project was to understand the behavior of butt weld jumbos profiles submitted to fatigue loading and to develop a set of guidance rules that describes the behavior of these elements to fatigue resistance in arches of arch bridges. An experimental campaign consisting the automatic butt welding of the splices is presented in order to provide guidance on how to weld profiles with thick flanges and calibrate numerical models in terms of residual stresses evaluation after the welding. The access holes needs to be provided when welding such profiles, and a measurement of the residual stresses is proposed and compared with numerical results. On the right image, you can see the arch bridge conducted in Poland using heavy HD 400 x 314 in S355 grades. The length of the single span is 55 meters, and just to have an image of the weight and the size of the beams, for a total of 27 beams, the tonnage was 54 tons. The key advantages of using net arch bridges with hot-rolled HD section is that they have an aesthetical and slender design. In combination with higher grades like S460 or High-Star 460, lighter sections with reduced cross-sectional area are obtained. This translates into less welding volume than for welding hollow sections, reduction of constructional costs and environmental impact, easy connections of hangers, excellent inspections during operation because there are no hidden details, span lengths for road bridges up to 120 meters and for railway bridges up to 100 meters. Such profiles can be used in combinations with composite and pre-stressed concrete decks. It is a recognized solution in Poland, and in the here under images you can see three examples of bridges using HD profiles. First one is WD 137 bridge, completed in 2009 and consisted of two independent constructions, each deck having 72 meters span. The rise to span ratio of the arch is 13.94 meter and the spacing of the arches is 8.62 meters. The arches were designed from HD 400 x 744 grades S460 rolled sections. In the middle, you can see the bridge WD 431, and the object consists of two independent constructions, and each one carries one interchange slip road over the motorway. Theoretical span of each construction is 62 meters. Rise to span ratio of the arch is 9.3 meters, and the arch were designed from hot-rolled UC profile sections in S355. The deck was designed as a concrete slab construction with longitudinal pre-stressing. And the last one, in the right, WD 57 bridge, again in Poland, had its detailed plan for construction completed in September 2009. The viaduct has a span of 75 meters. Rise to span ratio of the arch is 12.89 meters, and the arch was designed from HD 400 profiles sections in S460 grade. In this slide, I present another bridge that used heavy HD section constructed in Poland. The flange thickness that were used was 125 millimeters, and according to the US design code AWS D11, access hole needs to be provided to be able to connect the beams between. The geometry of the access hole is according to this guide and you can see them in the top left image. The main question is, what is the best geometry that can assure an optimal behavior to fatigue loading? So to answer properly to this question, an experimental investigation has been conducted and consisted in 2 steps. First step, welding of the splices at in situ Residual. The analyzed section consisted in an HD profile in high star 460 grade, having the flange thickness of a 90 mm. The automatic welding flux core arc welding process was used, and the welding sequence was alternated between the upper and the lower flanges and at the second stage in the web in order to avoid additional constraints in the connection. The reason of performing automatic welding was to control better the welding parameters that are presented in the top middle table. In total, there were used 384 passes, and the preparation of the profiles before the welding is presented in the bottom right image, and the geometry of the cope hole is according to AWS design code recommendations. As mentioned, the welding sequence was alternated between the upper and the lower flange in order to avoid additional constraints in the connection. The irregularities in the edges were avoided by welded run-on and run-off pieces at the extremities, allowing the weld to continue beyond the intended length. The stiffeners added before the welding were removed in the last step. The welding setup is presented in the top right picture. The measurement of the residual stresses was performed at University of Liège using the traditional slice method. Measurements were performed in the weld, in the heat-affected zone, and in the base material. The measurements of the lengths are first made on the initial uncut piece, after the other measurements are carried out during the slice cutting. The stresses were calculated for each element based on the total elongation, and finally the distribution of the residual stresses in the section is obtained. The flanges and the web are cut in 70, respectively 12 pieces, cut alternatively, center in the weld S and eccentric HS. The goal was to see if there is a difference between these 2 zones. In order to measure the stresses in the access hole area, it was used the rosette method. In this method, the micro deformations were measured using the 4 gauges placed near the edge of the access hole that measure the deformation in the 3 directions of the rosette. The numerical simulation was made considering a multi-pass automatic welding process connecting 2 segments of the beam. The procedure was based on the input from the French Institute d'Etudes results, which performed the welding of the specimen for experimental testing and documented the procedure. The weld module interface AWE, an Abacus plugin, was used to perform the welding simulations. It automatically creates all the analysis steps, energy transport boundary conditions, and builds the thermal model, followed by the automatic generation of the corresponding mechanical model for stress analysis. The material in the numerical model was defined according to input data from tensor tests together with mechanical specifications and temperature variation properties. The temperature variation properties were based on the European standard Eurocode 3 Part 1-2, and kinematic hardening stabilization option was used for the plastic input in Abacus. In order to consider the cyclic loading induced by the welding process, heat and cool down causing expansion and contraction of the material, and to correctly define the mechanical properties of the model, 3 different material zones with different properties were defined. The heat transfer model shows the variation of temperature throughout the welding procedure. The directional stresses were obtained in the orientation of the beam axis and show peak stresses located in the base of the flange and transition area of the web base and weld material due to local mesh distortion of beam contraction. In this slide, I present the comparison of the residual stresses. In the flanges, it can be observed that the residual stresses values obtained using the numerical model are overall aligned with the experimental outputs, with a concentration of stresses in the beam flange extremity where the appendices are welded to the beam. The biggest discrepancy between the numerical and experimental directional stresses is located in the middle layer of the flanges, which is explained by the fact that this is a region of stress transition between compression and tension. In the web area, the output results of the numerical simulation show considerable differences up to 200 megapascal when compared with the experimental tests, as after various examinations, the preliminary conclusions show that since the welding procedure is made in stages, the weld of flanges imposes a contraction of the beam in both directions before starting the weld of the web, which causes distortion in the web mesh area, and further investigation needs to be made. In the access hole region, you can see in the upper image the position of the rosette, which is at the extremity of the access hole, and then in the under image you can see that the peak was not obtained in the same position where the rosette was placed. So there was a difference in the value in the experimental and numerical value between these 2 points. And as a last point, a study of the welding concentration in the access hole having different geometry has been made. So the main objectives of the study was to evaluate the concentration of the stresses in the access hole having different lengths, and a set of 2 sections, and in total 28 models were evaluated, and the length versus the position of the access hole varied. According to the previous results, it was possible to conclude that the stress factor at the access hole area do not present significant variations with the size of the section and tend to stabilize around 100 mm length of the cut section. So to conclude, HG sections in net arch bridges represent a clear trend due as more economical and aesthetical design is required. Thanks to the presence of access hole, the stresses due to the shrinkage in the weld are reduced to a minimum, and three-dimensional effect together with stress concentration are avoided. Overall, the comparison between the longitudinal stresses from numerical and experimental tests show a good consistency. The stress factors at the access hole area do not present significant variations with the size of the section and tend to stabilize around 100 mm length of the cut section. Application in other countries than Poland is possible due to the attractiveness of the solution, and the next step is to finalize and to determine the VAT category using structural hotspot concept on the numerical models already created. Thank you for your attention, and if you have any questions, feel free to ask them.